Welcome to this lecture. In this course, so far we have looked at schedulers, task schedulers, and we said that task scheduling is possibly one of the most important activity of a real time operating system. And we started looking at some simple real time task schedulers. Those goes by the name clock driven schedulers. So, those are used in very simple applications where the processing power, memory, etc., are very small. The operating system itself is only a small program, takes very little memory and computing power. We looked at the table driven scheduler and spent couple of lectures on cyclic schedulers, because cyclic schedulers are an important category of schedulers used extensively. And then we are looking at the event driven schedulers. The event driven schedulers are an important category of schedulers used in larger applications where the number of tasks are more and the operating system uses significant processing overhead and also memory footprint. We said, if you remember in the previous lecture, that there are large variety of event driven schedulers, but then all of them are variants of two basic categories of schedulers. One is the EDF, earliest deadline fast, and the second is RMA, rate monotonic algorithm. The EDF is the optimal scheduler, it is a dynamic priority scheduler, and we started looking at the EDF and we were trying to find out its difficulties, because EDF, even though it is a very good real time task scheduler, it can schedule, it can have successful feasible schedule for tasks which no other schedulers can schedule. Its overhead is small, but then it is not used in common applications. The reason are its shortcomings, and we were looking at the shortcoming, three major shortcomings. One is that if there is a transient overload, some task gets delayed, maybe because it is waiting for some signal, maybe it just went into a larger path in the code, maybe it went into a non terminating loop, whatever, but then if that happens even to a very non critical task, very routine task, still the most critical task can miss its deadline. So, that is one major problem with this. The second is runtime inefficiency. The other schedulers are much more efficient. For example, the RMA based schedulers are much more efficient. Let us see the source of inefficiency of the EDF scheduler. So, if you remember, at every scheduling point the scheduler becomes active and then selects the next task to run. In the EDF algorithm, it checks all the ready tasks, find out which has the earliest deadline. To do this, it must have the tasks in some data structure. Let us first examine if all the tasks are ready tasks are waiting in a queue. So, you need to traverse the queue and find out which is the task having the earliest deadline. Traversing a queue is order of n, if n tasks are there. then O n is the complexity of finding the task. Of course, when a task gets generated, inserting in the queue is O 1 because it gets inserted at the end of the queue. O n at every scheduling point is actually inefficient. We should ideally have O 1 as the complexity, because if the tasks are more and the scheduling points occur very frequently, every few microseconds or so, then the runtime overhead becomes significant. Now, let us see what are the other options for implementing the EDF scheduler. One is a priority queue. If you can recollect what is a priority queue, it is the one, it is a type of queue where the highest priority task is available at the top of the queue. So, finding the task having the shortest priority is O 1, but then what about inserting a task? If you look into the complexity of inserting into a priority queue, find that it is log n. So, even though it is a better structure than a singly linked list, a linear queue, but still log n is not a very desirable time complexity for a task, for a scheduler. Therefore, we can say that EDF is not really very runtime efficient. The most important shortcoming that is faced in a application, real time application development, is poor resource sharing support in EDF based scheduler. In a practical application, the real time tasks need to share resources. Resources can be some data items based in memory, it can be open files, etc. So, these are called as the critical sections. If we look at the solutions that exist for resource sharing among tasks in EDF and critical resources we are talking of, then the solution is extremely inefficient, and this causes the tasks to miss their deadlines. As we proceed in couple of lectures, we will examine the issue of resource sharing. We will see that for the rate monotonic based schedulers, very good algorithms are available for resource sharing, but for EDF resource sharing is a big problem. We do not have a satisfactory solution to that, and possibly that is one of the main reasons why EDF is not used in practical real applications. But then before concluding our discussion on EDF, let us look at one point, that is we have so far assumed that for every task the period and deadlines coincide. The period is equal to deadline, but in many situations, not many, but then in some situations, the deadline and the period can be different. For example, deadline can be less than the period, or in rare cases deadline can be more than the period. So, in these cases, how do we check EDF schedulability? One solution is to take the minimum of P I d I. So, E I by minimum of P I d I, that gives the utilization, and see that that is less than 1. So, this is a sufficient condition. That is, if this is satisfied, then of course, the task set is schedulable in EDF, but then it is not a necessary condition, because we can find that some task set is not meeting this criterion. This is too strict a criterion, minimum of P I D I. It does not meet the criterion, but then still it may be possible to feasibly schedule this. We will not go into details of that, but just to know that if P I is not equal to D I, then we need to use E I by mean P I D I, which is a sufficient schedulability condition, but then there can be some cases where they do not meet this criterion, but still become schedulable. There are some variations, actually many variations of EDF. One important variation is called as a minimum laxity first. In EDF, we look at only the deadline, how much deadline is remaining, but then we do not consider how much execution time is required over the deadline. If the deadline is 100 microseconds and the computation time required is 5 microsecond, compared to another task whose deadline is 100 microsecond, but the computation time required is 50 microseconds, then it may be better to give higher priority to the task having more computation left over the same deadline. That is the main idea here in the MLF. So, here the laxity is defined as the deadline minus the time required to compute the task execution, and this turns out to be a good algorithm, because we are considering the task that is most likely to fail fast is assigned the highest priority, and it performs at least as good as the EDF, but then in some cases it can perform better than EDF. Now, we have concluded our discussion on EDF, the earliest deadline first algorithm, that is the optimal scheduling algorithm. Now, we will start discussing the rate monotonic schedulers. These are, I think, the most important class of real time schedulers. Even though these are not as proficient than the EDF, but practical implementation of these is much simpler and also more efficient, and the other shortcomings of the EDF like resource sharing and so on become easy here in the rate monotonic scheduler, and therefore, these schedulers are used extensively in many real time applications. The main idea in the rate monotonic scheduler is that the priority of a task is proportional to its rate of arrival. Let me repeat that. Here the priority is statically allocated by the programmer or the designer, and the priority that is assigned to a task should be proportional to the rate at which the task arrives or the proportional to its frequency. If a task the period is 2 millisecond, it should definitely have higher priority compared to a task whose period is 10 millisecond. So, the higher the frequency or lower the period of a task, the higher should be its priority. That is the basic premise or the basic algorithm for this scheduler. So, if the frequency or the rate of arrival or whatever we give name to this, if we arrange the tasks in this order, then the priority should be increasing in order of their frequency, or decreasing in terms of their period. So, the priority is a increasing function of the task arrival rate. Just to give an example, look at the task 1, it is repeating frequently, rate of arrival is very high compared to the task 2, rate of arrival is lower, and therefore, task 1 has higher priority and task 2 has lower priority. And the essence of this scheduler is that the higher priority task will preempt any lower priority task and start running on its arrival. So, let us look at this actual execution, whether that is happening. At time 0, both task 1 and task 2 instance are ready, but then task 1 has higher priority and therefore, this instance starts running. The task 2 instance has to wait, and then as soon as the task 1 instance completes execution, then the task 2 instance starts running, and then the next instance of task 1 arrives, it preempts the task 2, starts running, and then as it completes, the task 2 again becomes active, and so on. So, as long as there is a higher priority task, the lower priority task cannot run, and it is the higher priority task that runs. That is the main concept in rate monotonic scheduling. One important result is that among all static priority scheduling algorithms, RMA, the rate monotonic algorithm, is the optimal algorithm. So, if RMA cannot schedule a set of periodic tasks, no other static priority scheduling algorithms can. But on the other hand, any task set that is scheduled by any static priority task scheduler can also be run under RMA. So, RMA is a very good static priority algorithm. Now, let us spend some time on the results that are available on the schedulability analysis. So, that is, given a task set, can we say that it can be feasibly scheduled on a rate monotonic scheduler? So, those results are typically given as utilization bounds. What is the utilization of the task set for the processor, and based on that we can conclude whether it can run feasibly on a processor under the RMA scheduler. The first result available since long time, 1971 I think, is called as the utilization bound one. Okay, this is the basic result. So, this is available since long time, that the utilization is less than 1, obvious, because utilization of a processor cannot be 1, and this is natural that the sigma E I by P I should be less than 1, and this is a very basic condition called as the utilization bound 1. This is a necessary condition, but then a task set meets this E I by P I, sigma E I by P I is less than 1, where E is the execution time and P is the period. We need to check further conditions. Just because task set has met this condition does not mean that the task set is schedulable. But if you remember, in the EDF schedulers, this was both the necessary and the sufficient condition. The same expression sigma E I by P I less than equal to 1 was both necessary and sufficient condition for the EDF schedulers, but here it is just a necessary condition. We have to first check whether E I by P I sigma is less than 1, then we can look for other utilization conditions. Otherwise, if even this condition is not met, obviously it will not be schedulable under the rate monotonic algorithm. The second result is again a utilization bound available for long time. 1971, Liu and Leyland proposed in a landmark paper that the utilization bound should be less than n into 2 to the power 1 by n minus 1 for a task set to be schedulable. So, if there are 10 tasks, so 10 into 2 to the power 1 by 10 minus 1, the utilization sum of utilization of due to the tasks should be less than that. Of course, you can check that it is always less than 1, because even if n is equal to infinite, so infinite into 2 to the power 1 by infinity minus 1. So, that is a indeterminate form, but if we use the L'Hospital's rule, we will find that it is 0.6. We will come to that. Let us see how the utilization bound varies with number of tasks. If n is equal to 1, then it becomes 1 into 2 to the power 1 minus 1, which is 100%. So, if only one task is there, then even if it has 100% utilization of the processor, still it can be schedulable under the rate monotonic algorithm. But what if there are 2 tasks? It becomes 2 into 2 to the power 1 by 2, that is square root of 2 minus 1, and square root of 2 is 1.41, minus 1 is 0.41 into 2 becomes 0.82. So, from 1 it becomes 0.82 with 2 tasks. For 3 tasks it further reduces and so on, but finally it saturates at some value. Let us find out what is this value, because according to this expression, it as n increases, the number of tasks increases, the utilization at which the task set is schedulable decreases. So, this is the behavior. If we really take number of tasks 1, 2, 3, 4 etcetera, we will see that by the time there are 10 tasks, it almost settles in this 0.7. So, 0.7 or 70% utilization, if a task set has more than 0.7 or 70% utilization, we can safely assume that it is schedulable. So, if sorry, I need to state what I said, that if the utilization is less than this, if the utilization is less than 70%, anywhere in this region, all the tasks that are utilization is in this region, that is less than 70%, this is the upper bound of utilization actually. So, as long as we find that a task set the utilization is less than 70%, we can conclude that it can be feasibly scheduled by a rate monotonic scheduler. As given by this Liu and Leyland bound, the maximum utilization at which the tasks become schedulable falls as the number of tasks increases, and for very large number of tasks it settles at around 0.7. To be precise, it is 0.692, and how do we get as 0.692? It is based on the solving the indeterminate form infinity to the power infinity into 0 indeterminate expression. Applying the L'Hospital's rule to this indeterminate expression, we get log 2, which is 69%, 69.2%. The main thing to note here is that as long as the task set the utilization is 69.2%, we can safely say that the task set is schedulable under Liu-Leland bound. But if it is not schedulable, its utilization is more than 69.2, then we have to check how many tasks. If the task is, let us say, 2, 3, 4, etc., then we need to compute this expression n into 2 to the power 1 by n minus 1, as I was mentioning, that for 2 tasks even up to 82% utilization, the task set can be feasibly scheduled by the rate monotonic scheduler. Because the rate monotonic scheduler is an important class of scheduler used extensively in many real time applications and also supported by almost every commercial real time operating system. We are just trying to study this scheduling algorithm slightly more carefully, and the next lecture we will continue from this point. We will conclude now for this lecture. Thank you very much.